Number 7, referring to the example combining series and parallel circuits in figure 21.6, calculate I3 in the following two ways. Yeah, we're not going to do that. What I'm going to do is I'm going to take this circuit, which is represented by that from the book, and I'm going to calculate everything. All right. In other words, I'm going to calculate the voltage over this resistor. I'm going to calculate the current flowing through that resistor, and I'm going to calculate the power dissipated by that resistor. Everything. Okay. So if you know how to do this, you can do any problem. Now, the only thing is, though, that, you will want to do practice, because how I'm going to approach this and how I see it can be challenging at the beginning. All right, but that's where the practice comes in. So let's first start out by doing this. My goal in any of these problems, when I want to find out, current flowing through this or voltage over this or whatever the case is I want to take this complex circuit and I want to simplify it. I want to get this whole circuit that has 3 resistances down to a equivalent circuit that has 1 resistance. Okay, that's the goal. Now, what you have to do is you have to now work in parts. We realize that this element is in, let me highlight it. This element, this resistance, is in series with this parallel arrangement, right? That's a little confusing, I know. But this resistance is in series with, because it's directly flowing through this component, right? So those two pieces, this piece and this piece, are in series. Also, to further complicate matters, these two now resistances are in parallel with each other. Notice that I'm talking about relative relationships. In other words, this resistance is in series with these two. But these two resistances are in parallel with one another, almost in series. So what we need to do is we need to work with the simplest element possible. Do you think it's easier to simplify this series element with this, or I should say this element with this series element that is comprised of a parallel element inside of it? No, it's not. Let's just work with this one element first. Let's work with this particular piece, okay? This piece right here. What I want to do is I want to simplify that parallel arrangement to an equivalent resistance. In other words, what I want to do is I want to create an identical picture. Okay, so watch what I'm going to do. I want to create an identical picture, except for the fact, and I realize I'm going to have to resize it, sorry. Except for the fact, and let me just resize this for 1 second. Hopefully your semester's off to a good, probably start. You might be a little bit into it by now, and I'm getting distracted. So enough with the chatter. So I'm going to create an identical circuit, except for the fact that I'm going to combine this parallel arrangement into one equivalent resistance. So watch what I'm going to do. I'm going to erase this. Okay? Erase it. Boom, 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 boom. Okay? Erase it. And what you're going to do is you're then going to replace it now with a single resistance. Just like that. Okay? I'm going to call this R. It doesn't matter what you call it. All right? Call it R sub P if you want. Okay? Doesn't matter. But what I need to do now is I need to solve for this, or let me actually do it this way. Let me do it R sub EQ1. In other words, this will be the equivalent resistance, and I just labeled it 1 because that's the first thing I worked with. Okay? So what I need to do is I need to figure out this equivalent resistance. In other words, this parallel arrangement, all right, of resistors will be equivalent to a single resistance placed in that spot. But how can I calculate that? Well, that's the whole point of these two formulas over here. That's what they calculate, okay? This is talking about the equivalent resistance in series, and this variable right here is talking about the equivalent resistance in parallel. Now, I know I'm dealing with a parallel arrangement here, so what I'm going to do is I'm going to then calculate the equivalent resistance in parallel. In other words, I'm going to use that formula, 1 over R sub P. And you can call this 1 over EQ sub P. In other words, 1 over the equivalent resistance of the parallel component. Doesn't matter. Is going to be equal to R1 plus R2. Sorry, 1 over R1 plus 1 over R2. However many you have, it doesn't matter. Blah, 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 blah. Now, in this particular case, there's only 2 of them, right? Because I'm just focusing on that part of this circuit. So R sub EQ P is here, but I called it 1. So this will be 1 over now the first resistance of 6, doesn't matter which one you put first, plus then 1 over 13. Now do the math. So the math is going to now be 1 over 6 plus 1 over 13. So this works out to be 0.24, yeah, 6, excuse me, 4 or so. Now, we don't want to know 1 over REQ, we want to know REQ, right? So what you got to do is realize that this is really over 1, and I'm then going to, if I flip this side of my fraction, I'm going to flip that side. So basically this now works out to be REQ over 1, but that's just the same as saying REQ, right? Is equal to 1 over 0.244, okay? Calculate that. So take the inverse, basically, of your answer. I'm going to use the exact value in the calculator. So this works out to be 4.11-ish, okay, 4.11. And that is now in terms of ohms. So what I just found is I just found now the value of this, okay? That's what I did. This is equal to now 4.11 ohms. And I'm going to highlight that in yellow, okay? I'm going to highlight that part in yellow. All right, so these two resistances that I'm highlighting right now, let me do that again. These two resistances in parallel are equivalent to a single resistance of 4.11 ohms. All right, that's what we just found. Now, let's get rid of all this work. And we're getting closer, right? We're simplifying the circuit, if you noticed. But now, it's not totally simplified. Now you want to ask yourself, well, how are these two resistances related? You know, are they connected in or related in series or in parallel? So just trace your pen or pencil or whatever, your finger across the screen. If you flow through this resistor, you don't have a choice but to then flow through that second one, right? That's series. That's all it is. They're connected in series. The current has no other way to flow, okay? So now I know these two resistances are connected in series. And therefore, I can now find an equivalent resistance, okay, between the two. So what I'm now going to do is I'm going to copy this, okay? I'm going to copy this picture. And instead, though, of having two resistances in this circuit, because I know that they're in series, I can write an equivalent resistance now. And it doesn't matter where you put it. You could put it here if you wanted and then just connect this on around. You can make it look a little more symmetrical and connect it here. It doesn't matter. Not at all, okay? What I'm going to do now is I'm going to call this R sub EQ2. And I'm going to highlight that in green, okay? So this now, all right, this equivalent resistance is going to be equivalent to, I'm going to calculate the equivalent resistance to this resistor in series with this resistor, okay? That's what I'm going to do. Now, how do we do that? Well, these two are in series, and therefore I use my series equivalent formula, right? So this just says that the equivalent resistance in series is going to be equal to R1 plus R2. This is nice and easy. So in other words, my equivalent resistance number 2, is that's what I called it, is going to be equal to the 1 ohm plus then the 4.11. So now when I add those two together, we're going to get simply 5.11 ohms, okay? Now that value is this value, okay, 5.11 ohms. Now basically what I did, okay, is I found now and I simplified this complex circuit now into this simple circuit. This whole complex circuit acts as if there is a single resistance on it that has 5.11 ohms. Obviously, they are not identical, though. This has 3 resistances and this has 1, okay? But this simple now circuit acts as if it is this complex circuit, okay? Or in other words, it might have been make more sense to say this complex circuit acts as if it has a single resistance on it that has a value of 5.11 ohms. Now what this does, I worked from complex down to simple. Now what I'm going to do is I'm going to work from simple backwards to complex, okay? So let's get rid of some of this work. What this now allows me to do here, looking at this simple circuit, is we have a single voltage, we have a single resistance, and therefore we can calculate possibly a couple of things. Most important here that I'm going to calculate is the current, okay? Now the current here, we know through Ohm's law, is going to be equal to V over R, or the voltage divided by the resistance. If If I have 1 voltage, 1 resistance, finding the current flowing through this very, very simple circuit is very, very easy. So this is simply going to be 12 volts divided by 5.11. And when we do that, we have to make sure we're going to be using the exact value in the calculator, okay? So it's really 5.10526, blah, blah, blah. So it's going to be 12 divided by that value. And this works out to be 2.35, okay? 2.35 amps. So that's the current now flowing through this circuit, okay? The current flowing through this circuit now, boom, 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 is going to be 2.35 amps. 2.35 amps, okay? Now, we have to remember, when we now look backwards to the next more complicated circuit, we have to remember that this now was a series arrangement between these 2 resistors. And if we found the current now flowing through an equivalent resistance of these 2 resistors in series, we know from doing a couple of problems prior now that the current flowing through this is going to be constant and equal to the current that I just found, 2.35 amps. Okay, flowing through each of these 2 resistances. So in other words, what I'm going to do is I'm going to now write this as I. We'll call this I1, and this will be equal to 2.35 amps. Okay? I'll call this now flowing through there. I'll call that current flowing through there I sub EQ1 is 2.35 amps, okay? 2.35 amps. Okay. Now, I was going to ask, do you have any questions? But I won't know if you do. So, we are now beginning to work backwards, right? Now, let me get rid of this simple circuit because we really don't need it anymore, okay? Now I keep working backwards, okay? What I realize now is I actually know everything I need to know about this single resistance. All right, I know the resistance. I know the current. So couldn't I find voltage? Right? Couldn't I find voltage there? Of course I can. If you know the resistance now flowing through, if you know the resistance of one resistor and you know the current flowing through that resistor, you can find the voltage of that single resistor by using Ohm's law. V is equal to IR. So voltage is equal to now the current, 2.35, multiplied by that, resistance. And that's simply going to be 2.35 volts. So that is the voltage over here. Okay, so what I'm going to do is let me just move this around a little bit, and I'm going to put that maybe in blue. A little happy blue. And we'll call this V1, okay, technically. So this is 2.35 volts. You know what we could also do now? Couldn't we find the power? I mean, we could have found that before too, but we could find the power if we wanted. So how could we do it? Well, use whatever you like. Whatever point, you got a whole bunch of values, use whatever you want to use. So the power here is going to be equal to, you can use IV, you can use V squared over R. They're all going to work out to be the same. Doesn't matter. So maybe we'll use IV. Okay, the current here is 2.35 and the voltage is 2.35. So we're just going to basically square it. Right? So square that value, it's 5.2. So, sorry, 5.52. All right, so P1, so maybe, let me start doing this. P1 is going to equal about 5.52 watts. And by the way, why don't we calculate it a different way? Let's do the V squared over R. Let's do V squared over R here. So it'd be 2.35 squared divided by 1. Oh, wait a minute, that's the same. You see? So that's P1. V1 was going to be 2.35 volts. I1 is going to be 2.35 amps. And then R1 was 1 ohm. Okay? So we'll keep that with us. Let's just get rid of this picture on the upper right-hand side because we don't really need it anymore. So now what we're going to do, okay, is now that I have all that stuff written down, all right, I'm going to now, let me erase this. And what I'm going to do because we don't really need it anymore. All right, it's just going to be, it looks confusing, and it's just noise at the moment now because we figured this part out. Okay, so let's delete that. And I'm going to try to pull this green thing out, this green highlight. Hopefully I just, oh no. Oh, there we go. All right, so don't even worry about that. We found everything we needed about it. Okay, now we're going to do the same thing. Now what I got to do is I got to go backwards again. I know the equivalent, I know the current flowing through this resistor. I know the equivalent resistance of this resistor. So what can I find now? Just thinking about knowing the current, the equivalent current here, knowing the equivalent resistance, I can essentially find the equivalent quote-unquote voltage, right? I could use V is equal to IR. I can call this my equivalent voltage, whatever, or total voltage over, it doesn't matter. It doesn't matter what you call it. So the current here is going to be 2.35 multiplied by that equivalent resistance, which was 4.11. Now, let me go back and get the exact value. Okay, so it wasn't exactly 4.11, it's 4.105 to blah, blah, blah. So we'll take that and multiply it now by the 2.35, multiplying those exact values. So get a value now, voltage of 9.65. Okay, 9.65. Cool, volts. Okay, so that's now what we did was we found the total current flowing through this equivalent part. In other words, I found the total current, look back up at the top now. I found the total current flowing through this thing. Right, I found the total current, it's 2.35. But it won't be 2.35 through this piece, and it won't be 2.35 through this piece. In total, it's 2.35. All right. What I also found now was the voltage over this entire parallel arrangement. Now, what's constant in parallel? Voltage is constant. So in other words, what I just found, if I know that this equivalent voltage over this equivalent resistance is 9.65 volts, and this equivalent resistance was calculated by simplifying a parallel arrangement, that then allows me to know that the voltage over number 3, resistance number 3, is 9.65 volts because it's constant. And the voltage over number 2 is also 9.65 volts. You see? Now, what that allows me to then do is, and there's a whole bunch of ways to calculate this, but now that allows me to calculate the currents flowing through each, right? I can calculate the current flowing through this now. So, watch. Current is equal to, this is Ohm's law, voltage over resistance. So the current flowing through resistor number 2 will equal the voltage supplied to resistor number 2 divided by the resistance of resistor number 2. So V squared, so that's going to be 9.65 squared. No, not squared. Sorry, this 2 is down here. It's not even squared, but for some reason I thought it was. And then divide that by 6. So this is now going to be equal to 9.65, roughly. I'm using all exact values, just be wary. So this is I2 will be 1.61 or so amps. I'm rounding, okay? So I just found now I2 is equal to 1.61 amps, right? Now what can I do? Well, I can also find now the current flowing through the other one. Okay? So I'm going to do the same thing, but for now this resistor. I know the resistance, I know the voltage, I can find the current. The same exact way, the current flowing through resistor number 3 will equal the voltage through or applied to resistor number 3 divided by the resistance of resistor number 3. And this is simply going to be 9.65 all over now 13. And this works out to be 9.6 divided by 13. So this is now 0.742 amps. Okay? Now, that's then the resistance, that's then the current flowing through this resistor, 0.742 amps. Now look at something. This value here plus this value here equals this value here. Do it in the calculator. Take those two values and add them together. 2.35, I got the exact value. Right? That's exactly what we're talking about. Do you see how this is working? Do you see how if I found the total current flowing through this equivalent resistance, I know then that the total current that's flowing around this piece better sum up to equal that total, right? That should hopefully make sense. I'm thinking if I speak more forcefully, it'll just make more sense in and of itself. But that's how it works, right? And we're going to show you a couple of other things. So now, last but not least, I can also find the power dissipated by each resistor. Okay? So how do we do that? So we can do it similarly to how we did it before. Okay? So we can now do it, doesn't matter. P equals IV, you can whatever formula you like. It really doesn't matter. P is equal to IV. So the power over 2 is the current 2, right? So this is the current through number 2 is 1.61. The voltage is going to be 9.65. And simply now calculate it. So 1.61 plus the 9.65. I really should be using exact values. Just give me 2 seconds while I go back and grab them. 9.65, 1 second. Where's that number? There it is. So, oh, I added them. Whoops. Sorry. Let's do that again. Times. So 15.5. So this is roughly about 15.5 watts. That's P2. Okay, so let's write down everything we know about the second resistor. So we know P2 is going to be equal to 15.5 watts. We know V2 was 9.65 volts. We know that I2 is going to be equal to, what do we got? Equal to 1.61 amps. And then we know the R2 was 6 ohms. Okay. Now let's do the same thing for number 3. Okay, let's just erase this. And we're going to write everything down. So this is 3, 3, 3. And P3 now is going to be equal to I3, which is 13. No. 0.742, sorry. 0.742 multiplied by V, which was the 9.65. I'm going to go back in the calculator and use the exact values. So let's see what we got. There's that value times then the 9 point whatever. And I get 7.16, right? So this is then 7.16 watts, all right? So now we can write everything down for P3. So P3 is going to be the power dissipated by that third resistor is 7.16 watts. The voltage of that third one is going to be 9.65 volts. The I3 was 0.742 amps. And then R3 was going to be 13 ohms. Now, if I wanted to find the total power dissipated by, let's just clean this all up now. Let's just clean it up. So we don't need any of this anymore, right? That's just to help us out here. So what we can do is now just go back and put this back in. Put this back in. And now this was R3 that had a value of, what was it, 13? And this was R2 that had a value of 6 ohms. I know everything now about this entire circuit. If I wanted to find the total power dissipated by the circuit, guess what I would do? Add these two together. Excuse me, 3 together. There's 3 of them. Add them all together. Right? The power dissipated by 1 plus the power dissipated by 2 plus the power dissipated by 3 is going to equal the total. All right? Also notice that the voltages add up too. Look, the voltage over this one, number 1, plus, now don't look at these two separate, but because the voltage over these two are constant. But plus, let's say the voltage over 2, if you added those two together, guess what you're going to get? 12. Huh? Right? If you added then these two currents together in parallel, right? These are the two parallel arrangements. If you added these two together, those two currents, you're going to equal then the current also flowing through the series element. All right? Hopefully this makes sense. So if you understand how to do this problem and you really think it through, the other problems are exactly the same workings. They just changed a little bit based on the organization of the resistors. All right. So what was that? 48 minutes? All right. So guys, I think I'm done. Yeah, so thanks for tuning in. Appreciate it. Please remember to help us out and subscribe. I hope I earned your subscription with this one. I do. If not, maybe I'll get you on the next one. Sure. Thanks, guys. All right. Take care. All right. I'll talk to you later. Bye.